Greetings and welcome. In today's video, we're going to do products and quotients of complex numbers, which we've already done before, but this time we're going to do them in polar form. So let's consider the product of two complex numbers. So if I have r1 times cosine of theta 1 plus I times sine of theta 1, and I'm multiplying this by another complex number, so I'll just call it r2 times cosine of theta 2 plus I sine of theta 2. Now, so let's see if I can multiply this out and simplify and see if I can get a nice, concise form here. So I'm just going to rearrange things. So r1 times r2 is r1 r2, right? I think we're fine with that. And this cosine, sine, and cosine, sine, these two binomials, I'm going to multiply them out and literally like FOIL it out. So let's see. So I'll have cosine theta 1, cosine theta 2, plus I, well, let's see, I'll put cosine first again. Cosine theta 1 times I sine theta 2. And then multiply this one by that one, and I'll have plus, I guess I'll write it cosine theta 2 times I sine theta 1. And then multiply these two here, and I'll have plus I squared sine theta 1 sine theta 2. Alright, so with all of this, I can actually do some rearranging. I'm going to collect my real terms and collect my imaginary terms. So here's a real, here's a real. Oh, nope, I lied. Actually, at first glance, it might appear as though there's only this one real term because all of the others have i's in them. However, recall that I squared is in fact be able to be written as -1. So this is a real because the imaginary part disappears, and this is a real. So I'll combine these. So I'll have r1, r2. Let's see, this is all equal. So I'll have cosine theta 1, cosine theta 2. And this plus I squared becomes -1 times sine theta 1, sine theta 2, right? And I guess I'll put sub-parentheses around this. So this is my A for my result of the product of these two complex numbers. And now let's bring our other ones together. Plus, I'm actually going to factor the I out of both of these terms, I think. That's what I'll do. So I'll have, in this case, cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. And then close the overall big parentheses. Now, it turns out I can simplify these using some Pythagorean identities. So I'll have r1, r2 times this whole expression here is the cosine sum of angles identity. So that's going to be cosine of theta 1 plus theta 2. Just like that. This is a trig identity. And this whole thing is a trig identity. So it's plus I times, this is the sine of the sum of angles identity over here. So this will be I times sine of theta 1 plus theta 2. So it turns out this is the product of two complex numbers in polar form. And I think it's kind of a really cool little simplification. All I'm going to do is multiply the moduli, if that's a way to pluralize modulus, and I'm going to add the amplitudes, right? And it's kind of really, really nice. So let's do an example of this then. So that was just deriving it. So let's multiply the following. What if I've got 3 times cosine 7 pi over 6 plus I sine 7 pi over 6. So I want to multiply that by 2 cosine of 2 pi over 3 plus I times sine of 2 pi over 3. And then after I multiply it, so here's part A, and then part B will be right in rectangular form. So we'll convert it back out of polar form. All right, so let's do part A. So multiplying these two things, I could go through all of the work that I just did. Better yet, let's just use this kind of nice little formula. So my new R is just going to be R1 times R2, right? So R is just 3 times 2, or 6. Right? So that's not that bad. And my new theta is just going to equal theta 1 plus theta 2, right? That's what I got here and here. So my new theta, or amplitude, is going to be, what's that, 7 pi over 6 plus 2 pi over 3. And we're not afraid of a little bit of fraction work. So I need to find a common denominator here. It looks like 6 will do the job, so multiply this by 2 over 2, dose over a dose. So I'll get 7 pi over 6 plus 4 pi over 6, which I believe is 11 pi over 6. So now I can just write this as my answer. So the product of those two, I guess I could call it Z1 times Z2 if I'd given them names or something like that, will end up being 6 times cosine of 11 pi over 6. I always want to make the 11 into a pi as well, I don't know why. Plus I times sine of 11 pi over 6. And it actually wasn't that bad multiplying those, right? No as mas mal. And now the last step's part B. Let's rewrite this in rectangular form. So in order to do that, I just have to kind of evaluate these values of cosine and sine. So let's do that. So this would be 6 times cosine of 11 pi over 6. Let's see, 11 pi over 6 is in quadrant 4. Cosine is positive. I guess I'll rewrite this. This will be the same as cosine of pi over 6. The reference angle is pi over 6 in that quadrant. And then plus I times, and sine of 11 pi over 6, this is in the fourth quadrant. Sine is negative then, so that'd be the negative sine of pi over 6. So we'll simplify. 6 times cosine of pi over 6 is going to be, that's 30 degrees, so root 3 over 2, if I'm not mistaken. And this will be, well, I guess a minus sign here, if I simplify that. And sine of pi over 6 is just a half I. And then I could kind of simplify here. I guess partially cancel. 2 goes into 2 once and into 6 3 times. So I'll get 3 square roots of 3 minus a half I. And there it is in rectangular form, right? So I'm able to convert back and forth as I need to. And multiplying isn't that bad. So in order to multiply, you multiply the moduli and you add the amplitudes. Man, that sounds so great. Some alliteration there, if you will. Multiply moduli, right? Add amplitudes. Wow, it's genius. I love it. So yeah, so multiplying isn't bad at all. Let me go over into my next column, and now we'll talk about dividing. So suppose I want to divide my two complex numbers this time. So here's R times cosine theta 1 plus I times sine theta 1. And I'm dividing it by R2 times cosine theta 2 plus I times sine of theta 2. So in order to deal with this, well, an issue I have is the fact that I've got this I in my denominator. So I'm going to have to multiply by the conjugate of this problem part that I've got right here, and the conjugate of that will be cosine theta 2 minus I sine theta 2. Oh man, this is getting crazy, but don't be afraid. It's going to be okay. And cosine theta 2 minus I sine of theta 2. And multiplying by the conjugate is going to be helpful. The reason I'm doing this is because it is going to give me the sum and difference pattern, which gives me the difference of squares pattern, and that's going to actually conveniently work out for us. So let's see, what is this equal to? I'm going to actually separate this into two fractions. I'll have R1 divided by R2 multiplied by the other fraction made up of all these cosines and sines. And over here, I'll have to make sure, recognizing that this fraction bar or vinculum is a type of grouping symbol, I'm going to have to FOIL out all of this up top. So I'll have cosine theta 1, cosine theta 2. Let's see. Man, hopefully I leave enough space here. Don't want to write too large. And then I'll have minus cosine theta 1 times I sine of theta 2. Oh man, I feel like I'm running out of space already. This ain't no good. And then I'll multiply I sine theta times both of those over here as well. So it'd be plus cosine theta 2 I sine theta 1. And lastly, I times I, one's positive, one's negative, would be negative I squared sine theta 1 sine theta 2. Man, it's getting tinier and tinier, but hopefully you can read that. Whew, all over. Here, let me draw a better fraction bar. All over, and when I multiply these two things, once again, I'd have to either FOIL it, or better yet, let's just use the difference of squares pattern, right? So this would be A is the cosine theta 2, right? So that would be cosine squared theta 2. Minus B is the I sine squared theta, so that would be I squared times sine squared theta 2, right? So let's do some simplifying. So similarly to our previous derivation, I'm going to group, well, let's see, first of all, I know that I squared is negative 1. So I'm going to group the real parts, which will be this one and this one, and I'll group the imaginary parts, these two. So I'll have cosine theta 1, cosine theta 2. Now I squared is negative 1, minus a negative 1 is plus, right? So plus sine theta 1, sine theta 2. So there's my real part. And then let's see, this one, I'm going to factor out the I, and now I'm wondering how I want to handle this negative. I'm going to factor out a... Should I factor out a negative? No. No, I won't. Plus I times... And let's see. I'll write this one first. So this would be sine theta 1 cosine theta 2. And then this minus sign is sticking with this guy. And this would be sine theta 2 cosine theta 1, or whichever way you want to write it. It doesn't matter. Cosine theta 1. All over. And now check this out. Let's see. So I squared, once again, is negative 1, so minus a negative 1. I'm going to rewrite this as sine squared theta 2, right? This becomes positive, plus cosine squared theta 2. And I'm really excited about what that's going to be in just a moment. Perhaps you recognize it as well. And let's see, similarly, here is the cosine difference of angles. So this is going to simplify to being cosine of theta 1 minus theta 2 plus I times, and here's the sine difference of angles identity. So that's going to be I times sine of theta 1 minus theta 2. And wow, this is just a thing of beauty the way this simplifies. all over, what is this equal to, guys? Oh, I hope you recognize your trig identities. Sine squared theta plus cosine squared theta, that's equal to 1. So this denominator is 1. I don't even need to write a denominator here. We have figured it out. It is this right here. So in order to divide two complex numbers in polar form, our modulus will be the quotient of the moduli, and our angle, or amplitude, is just going to be the difference. And we've seen this symmetry of ideas before in terms of exponents. If I multiplied two things of the same base, I added the exponents, and if I divide two things of the same base, I subtract. So when we saw multiply in the previous example, I added the thetas, and when I'm dividing two things, complex numbers in polar form, I'll subtract the thetas. So it's got this really nice symmetry that we've seen in other properties of mathematics before. And I just think that's great stuff. Great stuff. So let's do an example of this, and we will be done. So let's see. Divide the following. What if I've got 12 times cosine pi over 4 plus I sine of pi over 4, and I'm dividing that by 4 times cosine of 3 pi over 2 plus I sine of 3 pi over 2. And then part B, we'll rewrite this in rectangular form. So let's figure this out. So my R is simply going to be the 12 divided by 4, which is 3. And my theta will be the difference of the angles, right? So the numerator minus the denominator's angle. Also an appropriate pattern that we've seen before. And in order to do this, we're going to need a common denominator. So I will have multiply by 2 over 2. And I'll get theta equals pi over 4 minus 6 pi over 4, which is negative 5 pi over 4. Right? So I can represent this now that I know the modulus and the amplitude. I can represent this as 3 times cosine of negative 5 pi over 4 plus I times sine of negative 5 pi over 4. And there it is, represented in polar form. I just divided those two numbers, and it was as easy as dividing the moduli and subtracting the amplitudes. And it's kind of not that bad. Let's see, so before I convert this into rectangular form, I just kind of want to give this a quick graph. So let's see, 1, 2, 3 is the modulus. The angle for this, negative 5 pi over 4. So a full 4 pi over 4 would be a full pi. So I believe this lands me right here, would be that point. So it's in quadrant 2. I'm expecting cosine to be negative in that quadrant and sine to be positive. And the reference angle is pi over 4 there, right? So pi over 4. And this is out 3 units, 1, 2, 3, right? So there's that point on the polar plane there. So to convert this into rectangular form, cosine of negative 5 pi over 4, as I said, will be negative cosine of pi over 4 plus I times sine is positive in this quadrant, so let's rewrite it in terms of its reference angle. And let's see, 3 times cosine of pi over 4 is root 2 over 2. And sine of pi over 4 is also root 2 over 2. And then I'd, wait a minute. I think I made a mistake on the previous problem. I believe I did. I'll go back and correct that in just a moment. Hopefully you caught it already. On the previous problem, I did not distribute 3 into both of those. Oh dear. Oh no. Oh my gracious. So I'd distribute 3 into both of these. Silly me. Salami. So negative 3 square roots of 2 all over 2 plus 3 square roots of 2 all over 2I is the location of that point in rectangular form. What does this mean? This means go left 3 roots of 2 over 2 and up 3 roots of 2 over 2, and that would give you that point. So that's where you could kind of find these A and B values in this graph. And like I said, I think I made a mistake on the previous problem. Yeah, check this out. I dropped my parentheses prematurely. Oh, how embarrassing. Classic. So let's see. Yeah, so this would become 1. Oh, shame on me. Let's erase that. It's still going to be negative, and I believe it's just going to be negative 3I, if I'm not mistaken. And that should do it. Yep. Well, so dividing and multiplying complex numbers in polar form, I think it's beautifully simple. It required the derivation of it required some of our imaginary number work. It required multiplying by conjugates. It required trig identities. It was just kind of a wonderful culmination of a whole bunch of different mathematical properties and identities that all came together in a really nice simplified form. So I like this stuff. And actually, before I close, there is some application of this done in if you're ever an electrician or doing electrical work. There are some formulas related to these values and would be helpful. There's going to be some problems tonight. I'm not going to do a full example on this, but E equals I times Z is the formula, and those represent current, impedance, and voltage. So let's see. And voltage. And these will be represented as complex numbers. And one of the interesting things that electricians do is in their world, I is J. Kind of some interesting symmetry there. Right? It's like a mirror world. So they would represent a complex number of the form A plus BJ. And in order to, if you know 2 of these things, you could solve for the other. And I just want to point out that's why multiplying and dividing these would be helpful. Because, for instance, if I knew E and I wanted to find Z, I would divide both sides by the impedance and divide current by impedance using the property that we just did, and that would give me the voltage, and so on and so forth. So, or if I wanted to find the current and I knew the impedance and the voltage, I would multiply these 2 using the first property we did, and that would explain that as well. So it's just kind of a real-world application of some of these properties that we just did. Anyways, thanks for watching, and have a great